Yeah, there could be an Arrhenius style problem on the test.
Can we do like a practice one on that?
Sure. Give me a practice problem to do.
Yeah.
Or, that last test I posted, if you have questions on that too.
The question, like the essay question, how do you define what complexes are formed in the reaction?
Oh, those, ignore those. Those were for something else. But there's 2 pages, but the second page is not relevant to your test. That was for something else.
Number 16, using a reaction coordinate diagram and the Maxwell-Boltzmann distribution, so how K change with T. So how
This is to the point.
just they draw in the picture, then so that's it.
Yeah, the Maxwell-Boltzmann distribution is going to be described by a curve that looks like this. What's the mathematics of this curve? Do you know what kind of mathematical function that is? You recognize it? This is called exponential curve. Exponential curve is going to be described by an exponential. And so basically, K, the rate constant, is equal to A e to the minus e sub A over RT. This is. Do you need to know the Arrhenius equation? Here's an example. Yes, the Arrhenius equation is here in one form. There are 2 other forms that you should know.
So you have to memorize
You don't have to memorize this, but I'm going to give you the equations, the integrated rate laws. I'm not going to tell you what they are, but you're going to have to figure out how to use it. And so this equation, you don't have to memorize this. But what does this equation describe? Where does EA occur on the Maxwell-Boltzmann distribution? There's some kind of cutoff here, right? In energy. Somewhere, It depends. This changes depending on what? No. EA doesn't change based on temperature. EA changes because the energy changes. No, the population doesn't change. EA stays fixed unless. What would change EA?
Oh, because catalyst.
A catalyst could change EA, or what does a catalyst do? Yeah, lowers. How does it lower the activation energy? Yeah, it makes the bonds easier to break. The weaker the bonds, the lower the EA. The stronger the bonds, the larger the EA. And so this is it. You could just explain it very simply, saying that, as bond strength increases, you expect, or something, you expect the EA to increase. Well, increasing EA means what happens to K? The K goes down. And so as this gets, obviously what's going to happen to the population as this gets bigger and bigger? Yeah, the population goes down. And so increasing EA, K goes down because the population goes down, right? Decrease in population. What was the question?
So
rest
how
of-
K change with T?
Oh, with T, okay. With T, K changes with T. Here it's inversely proportional, and so as T increases, what happens to K? And K increases because Of what? What does T do?
There's more population.
There's more population. So at higher temperatures, the curve shifts. The population stays the same, but the so this is high T. You know, at higher T, the population is going to go up. So increasing population. That's it. Other questions? No?
The 2-point equation that we use,
Mm-hmm.
I'm not sure, like when can we actually use that?
When you use that equation is if you have K at different temperatures. And so we just look at T and K. So T1, T2, K1, K2. K changes with temperature, right? And so at different temperatures, you'd expect a different K value. It's no longer a constant. Right? And so if you're given two, temperatures, and one K value, you could solve for the other K. Typically, a question like this comes like this, If you double the rate, how much would the temperature have to increase? Would you double the temperature? Do you think? Like if I double the temperature, I should double the rate of reaction. Is that true? No. We could see how they're related by just taking the natural log of both sides of this and then doing that trick. What was that trick I said that's commonly done? It's not really a trick, but it's just something that is done quite a lot. Should be in your notes. What was that?
Use K at that point.
No, we take the ln of both sides of this and then simplify that. But there's something to generate the 2-point equation. What did you have to do algebraically? It's common, so this is why I made mention of it. Is it in your notes?
K2 over K1, and then went up down.
Well, how do you get the K2 over K1? What did you do to get there? There's some equations that I don't bother deriving, but that one I've mentioned something about the derivation of that.
Usually E, like if K2 you have E to the E A
Uh-huh.
and
The thing is, the way you should do it is not just kind of read through it, but actually read through it and then kind of mentally think, what is he doing there? And then just make a little note in your notes, an annotation, Because I said, what are we doing? This is a common thing that's done to derive these types of 2-point equations. Normally we leave it in this form. The ln of K is equal to minus EA over R and 1 over T plus ln of A. Normally we leave it in this form. But what's the trick you can do to this to derive the 2-point? You could just graph it, that's fine. But rather than graph it, you could also you could rearrange this equation. How do you rearrange this equation? Subtract, right. Somebody, I mean, subtract what from what?
ln minus
Subtract ln of K2 or ln of K1, T1 from ln of K2, T2. So we usually do K2, T2, so we get something like this, ln of K2 minus ln of K1, right? That's the trick. So, you know, what I was thinking is you just say, oh yeah, you just do the subtraction, you know, subtract the two values and you can generate this equation, right? And so when we subtract the two values, we get the this form of the equation, which is ln K2 over K1 is equal to minus EA over R, 1 over T2 minus 1 over T1. Where have you seen an equation like this before? Have you seen an equation like this before in Chem 1A? Yes. What was that equation? No, it wasn't the real gas. What was it? Vapor pressure, I think it was. Do you remember vapor pressure? Just want to remind you which chapter. You don't remember the vapor pressure? No, actually, it's somewhere in there. It is, but it's exact same. ln of P2 over P1 is equal to minus delta H VAP over R, 1 over T2 minus 1 over T1. Don't remember that? Vapor pressure is also exponential. Do you guys remember vapor pressure curves? They're not linear. They're like this. And so the equation that describes this is the natural log function. And so we could have the vapor pressure at temperature 2, vapor pressure at temperature 1. And the typical homework problem with this was you already know one of the vapor pressures, right? Like for example, water. You know one of the vapor pressure and one temperature for water. This is a review of Chem 1A. I shouldn't do so much review because I'm falling too far behind in Chem 1B. But the vapor pressure that you should know is at 760 millimeters of mercury or 1 atmosphere. The temperature is 373 Kelvin. And so from that, you know, you can solve for the vapor pressure. Remember in Chem 4 and also Chem 1A, you use the vapor pressure curve. In Chem 1A, we did this. We did a linear interpolation between 25.0 and I think 26.0, right? We did a linear interpolation to figure out what the vapor pressure was. Maybe it was 24 point something, 25 point something. Do you guys remember that? Well, it really, the linear interpolation only works because we're taking a very small segment and assuming it's linear, but this is totally non-linear, as you can see. So if the gap here were too large, then our linear interpolation would totally fail. I mentioned this in Chem 1A in the lab. And if that's the case, we would use this equation here, right? Because this equation describes this. Rather than having one full-page table, remember that big table in the lab manual of vapor pressure water? You could eliminate that whole table and just substitute this with a mathematical equation, which would be the most concise definition of this table, which is this curve, which is this data. And so, yes, the form of this equation should look familiar because you've seen it before. You know, I think they called this, what do they call this equation here? You guys remember what they call this equation? The Clapeyron equation. Anyway, so this you know, this is different, right? Because this describes a totally different thing, but mathematically it looks very similar, right? The form looks very similar. And the only reason I'm bringing this out, if it was just one equation, I wouldn't bother, you know. You don't need to know how to derive it or anything like that.
Can you write
But-
out the name of the equation?
What?
The equation, did you say the name of that?
Just look it up. It's in chapter 12. What's because they switch the chapters on me. This is just
See that equation?
this edition. Chapter 12. Chapter 12, page 516. Clausius-Clapeyron equation, equation 12.2. They get a ln function and then they do the subtraction. So this is the first time you saw the ln function and doing the subtraction. This is the second time you're seeing it. Okay? Since it's the second, if it was the first time, I wouldn't bother. Probably. But now we see it again. And you know what? We're going to see it the third time in this chapter, chapter 19, right? And so that's why I bring it up. Because that's it. Anyway, so we could use this equation to figure out, when you use it is when you have either the activation energy and 3 of these out of the 4, or you have, these 4 here, but you need the activation energy. That's when you use it. So we could actually calculate. It's really easy to calculate the activation energy. All you have to do is measure K at 2 different temperatures. This is a lot easier than modeling some transition state in Spartan. Did you see the transition state you could model there, like bonds forming, bonds breaking? And then, theoretically calculate the activation energy. But here's an easy way to experimentally determine the activation energy. All right, other questions? This kind of thing, see, there's a question in the homework, The question in the homework is, if it takes like, what was it? I forgot maybe I should look it up, but it goes something like this. If it takes 60 days for your milk to go rotten, right, in the refrigerator or something like that, what must the activation energy been? Let's say outside the refrigerator it takes a day. Inside the refrigerator it takes 60 days or something. What must the activation energy be? And you're going, there's no time here, is there? There's no time here, huh? There's no time here, but we know that if the rate constant is twice as big, the reaction should go twice as fast. And so I wrote this also. Well, I didn't do any application. We do K2 over K1 is equal to, or actually it's not equal because they're different, but it's directly proportional to T1 over T2. And so we could do it in different ways. We could look, okay, that reaction is happening twice as fast, or it's taking twice as long. And that gives us this fraction. That's how we'd use this equation. I don't know if I put that milk. Was the milk problem in the homework? Yeah, okay, maybe I didn't assign it this time around. Good one to put on the test, right? You see, now you're thinking like, that's the way I was thinking, they might pick another problem in there, one that we haven't seen. And so that's why I looked at all the problems before. When you look at all the problems, that doesn't give that many options to choose from, Right. All right, what else? But a lot of these problems involve like other chapters, and if the problem is like half of chapter 7 type material, then I'm not going to put something like that on the test.
should be all chapter 14, or at least 80 or 90% of it should be chapter 14. Some of the advanced problems require you to go back to earlier chapters.
Is this supposed to be K1 over K2 and then T1 over T2? Or T2 over T1?
What?
That's right.
Yeah. If the rate is 2 times as fast, then it should take half as long.
So they're inversely proportional. Okay, other questions? You know, when you see everything initially, it takes time to digest the information and make the connections. You know, that's what you're trying to do, is trying to make the mental connections. Like, hopefully, you know, you've seen it enough that you could say, oh, yes, I remember something similar to this way back when. You know, and then all of a sudden you made a mental connection, and that tends to stick a little bit better. The same thing, you know, I wrote all these random things, and probably it's hard to connect all these things together. You know, but if you've seen them enough times, then it becomes easier to connect. And it's just, you know, repetition. Repetitively saying the same thing, it's harder to forget. For me, that is. You know, what was I watching? You know, those people who have the phenomenal memories, you know, including little kids, and they remember everything. You know, if you can remember everything, you're going to do good in the class. You know, and they do. No problem. I was reading a story about one person who said organic chemistry was so easy, you know, because there was a lot of memorization. Memorization is so easy for them.
How do you change it? How do you change the mind?
I don't know. The only thing I could do was just lots of repetition,
Like,
and even that, you know, it's hard.
sometimes you read a lot, and then suddenly you don't have time to read it anymore, and then you totally forgot.
Yeah, that happens.
So just like
That happens. That's why you start early, and then by the time, hopefully by the time the test comes along, you've seen it like 5 or 6 times. That's the only way I could remember. If I didn't go through it 5 or 6 times before the test, then I would have a hard time remembering. And so this is why I never studied from the book, because it was impossible to go through the book 5 or 6 times before the test. I always had to go off my notes, and if my notes weren't complete enough, then I was going to be in trouble because I wouldn't know that stuff. You know? And so for me, that's the only way I could do it. And the homework, you know, I kept this homework in a separate book and then reviewed that as well. But when I reviewed the homework, I didn't redo the problem. I just, you know, for each problem, I just made a little mental story about that particular problem. Otherwise, it'd take too much time. And a lot of problems I never did in the first place. I just read the answer and tried to remember, you know, little things about it. And then, as you remember those, then you can make connections to other problems, you know, problems where they're mixing up things, elements. It makes it a lot easier. Not everything you can get by just through memorization, obviously. Okay, any other questions? No?
can you do one?
3-1?
Yeah.
31?
Yes.
31 is, what is the approximate rate of reaction at t equals 75 seconds for the zero order, first order, and second order reaction? All right, so 31, did you do the other ones before that?
So The first one is first order, the second one is zero order, the third one is second order.
Mhm. All right, so for zero order, then, let's see, number 31, A. And so the rate is equal to K, A to the 0.
Yeah.
So this is just K. And so it doesn't matter what the time or the concentration is.
K, I found K is 0.01.
Okay, that would be the rate.
Yeah.
Okay, for first order, the rate is equal to Ka
1.
1. And so what we have to do is we have to find the concentration at this. And so what do we want? We want the rate at 75 seconds. And therefore we have to find the concentration at 75 seconds. To find the concentration at 75 seconds, we would use this, the integrated rate law. You know, ln at 75 seconds is equal to, ln of 8 at 75 is equal to concentration at 8 at time 0, which is equal to minus K, and then T is going to be 75 seconds. And so we should have the concentration of A at time 0, just solve for A at 75 seconds, and just plug it in here into the rate law to get the rate. For the second order, you would do pretty much the same process. Just the equations are different. So rate is equal to Ka squared. And then here you'd have to solve for A at 75 seconds, which is equal to plus K T, which is 75 seconds, minus 1 over A initial. Right?
Is it plus or minus?
Plus.
Yeah. So my question is, the initial, should we take from 0 or we take the initial 50? Like,
No, the initial is 0. 0 seconds is the initial.
or always like that or not? Like,
Always like that.
because sometimes I don't remember, like in the lecture you said like, oh, we have to do something like.
Well, that was
small
calculating the
intervals.
slope
Oh,
between two data points. And so we're looking at the data point, that was like here. We'll call this, time 0, time 1, time 2. If I want the slope for this segment, then, the initial time's 1, the final time's 2. And so here the initial would be 1 because I'm looking at this slope here. But the integrated rate law describes the entire curve from beginning to infinity. And so we would do the real initial.
okay, thank you.
So we always have to use the initial at time 0 when we do the integrated rate law?
Well, it depends. It depends because if you're doing K analysis, no. When you do the K analysis,
Small intervals.
you use small intervals, right?
But for the rate law, we have to
But
do
for the rate
actual-
law, when you have everything figured out, then you do the
Actual,
Yeah.
okay.
actual initial.
Thank you.
Okay, number 69. The reaction 2NO plus Cl2 yields 2NOCl has a rate law. Okay. KNO second order, Cl2 first order.
Right? KNO second order, Cl first order.
When you look at that rate law, it could be one-step mechanism, huh? It could be a one-step mechanism, right? And so that's always a possibility. Maybe it is a one-step mechanism. The only negative would be it's termolecular, but that's okay. It could still be a one-step mechanism, and this could be called a elementary process or simple collision. If that's the case, then we need, two NOs from Cl2, and that's why we got the second order in NO. But they're asking for a two-step mechanism, and they want a fast, reversible first step followed by a slow step.
So, let's go. We just try it, Maybe an NO collides with a nothing. Let's say an NO just collides with the wall or some inert gas particle. Unimolecular. If this is unimolecular, what could form? Nitrogen and oxygen. Does that look very good? No. Or nitrogen and maybe it forms oxide and nitrogen 2+.
No.
At least this is balanced. Some people will do this. Some people will put nitride and oxide. What's the problem with that? The charge is not balanced.
Is it actually easy to put like N2 plus O2?
You can't because there aren't enough. It's unimolecular. You just have one molecule that's going to break up into something. And so this is it. So does it look good? No. Unimolecular for Cl2. Yeah, that could happen. Cl2 goes to 2 Cls, maybe. Yeah, and then another one would be, this is a two-step. This would be 2 Cls with 2 NOs, 2 NOCls. But look at the collision in the second step. What kind of collision is that? Yeah, 4 species collision, which would be not very likely. We could be. But it's better if it were just a Cl and an NO. So we have a Cl plus an NO plus a Cl plus an NO. That would be a 3-step. This doesn't look like it's going anywhere. So we'll try bimolecular. Next. We tried bimolecular collision. We applied maybe an NO plus an NO. Now you could have N2 plus O2. There's no problem with that, because now we have enough atoms to make an N2 and an O2. And maybe this is good because N2 and O2 form a fairly stable mixture, it seems to be, in air. Yeah, and then what would we have next? We'd have, we can't get really a two-stepper because we get N2 plus O2 plus Cl2 yields.
Why was that Cl and NO didn't work?
Because this would involve a four particle collision. Yeah, 4-way.
So we have and like 2 and 1 only, 3 not working.
No, 3 works too, but not as common.
It's not like
Is it bimolecular collision?
So this one doesn't look like it's going anywhere. Okay, let's try something else here. What else can we have?
NO plus CO2.
NO plus Cl2?
yields NOCl plus Cl.
Well, let's do this one. Let's try exhausting all the possibilities here. This could form N2O plus O, or it could form N2O2. Yeah. Which one do you think will get us closer? Let me try that. We try N2O2. N2O2 plus Cl2 yields 2NOCl. This seems reasonable, right? Yeah, that's a big molecule, but it does exist. And so here we could just have this, two bimolecular collisions. This is totally reasonable. But would we get the right rate law? So this looks reasonable. Let's see what the rate law would be here. And so the rate is equal to K2 N2O2 Cl2.
So that one we just guess the second one is lower.
Yeah, this would be the RDS here.
So just guess, right? We just guess.
The first step is the fast reversible.
Okay.
Since the first step is fast reversible, then K1 NO squared is equal to K minus 1 N2O2. And solve for N2O2 substituted here. We're just going to get K prime NO squared Cl2. Which works. This works. Arthur, what did you get? You got NO plus Cl2?
NO plus Cl2 yields NOCl plus a Cl.
Okay, let's try that. And so this looks good. This checks out. And so NO plus Cl2 yields NOCl plus Cl. Okay, that seems reasonable as well.
And then the second step is NO plus Cl
Okay, NO plus Cl,
yields NOCl.
NOCl. Let's try this one out here. So the rate, the second step is the RDS, right? But in terms of this, there's one thing that might give you second thoughts about this. The one thing that might give you second thoughts about this is they're saying that the second step is a slow step, and the first step is fast. So what do you think is more reactive, Cl2 or Cl? Cl should be more reactive. And so, when we compare these two, NO being attacked by Cl2 versus NO being attacked by Cl, I think NO being attacked by Cl would be a much more aggressive reaction, much more energetic. And so, it's backwards, I would think. First step should be slower than the second step. Did you get the right rate law? Yeah.
So maybe that's from the solution value. That's what we're trying to use. The solution value has the proposed mechanism as well.
Oh, is it? This is the one found in the solutions manual?
Yes.
Okay. Well, maybe mechanistically, could be wrong. It depends, because you would expect it in terms of energy. When I'm thinking in terms of energy, I'm thinking purely in terms of thermodynamics, right? And so if I think about it in terms of thermodynamics, I would think that the energy here for this reaction is like this, and the energy for this reaction, is like this, because NOCl should be less stable than NOCl2. So it's less stable. And NOCl should be more stable than NOCl plus Cl. And so I'm thinking thermodynamically, the delta H for this should be bigger than the delta H for this. And normally that translates into a faster rate, but not always. Depends on what the activation energy here is for that transition complex. So maybe this one forms a transition state that's easier to achieve. But nonetheless, all we can say is, does this prove that this is correct? You know what I just said here? No, no, it doesn't prove. This one could also happen.
But how do you get rid of the concentration of NOCl?
How do you get rid of the concentration of NOCl?
The solution manager assumes it's zero.
Assumes the concentration of
Yeah,
NOCl.
close to zero, around roughly zero, so the solvent.
They're saying the first step is fast reversible?
Yeah.
Okay, so you're saying that you get K1NO Cl2 is equal to K minus 1 NOCl Cl. And then you're taking out this intermediate,
Yeah.
which puts NOCl in the denominator. And so here the RDS would be the rate is equal to K2 times the NO times the Cl. And substituting the Cl in there, we get that we're going to get the K prime. Let's go ahead and just call it K prime. NO squared Cl2 divided by NOCl. So you're saying what's going on with this NOCl? They can't assume it's zero because if it's zero, this would go to
That's the solution.
infinity.
Around roughly zero, then he just simply get a conclusion.
Should use zero more using method of initial rates.
It doesn't make sense to make this a zero because if it's negative feedback, then this would make the rate infinite. Well, anyway, if we can't, if the NOCl were 1, then yeah, it'd work out quite nicely. 1 molar.
But how do you prove it?
I think it's a mistake. I think it's a mistake in the solutions manual. So,
It also says it's assumed the concentration of NOCl is assumed to be constant.
Okay.
That-
Is assumed to be constant. That means we're neither producing it or consuming it. But the problem is NOCl is a product of this. It's not only if it were if it were an intermediate, maybe it would be fairly constant because it's being formed and being consumed at about the same rate. And so what you're pouring in is what's pouring out, basically. And then it's fairly constant. If it's fairly constant, then what you could do is you could wrap it into K and call it K double prime.
That's what they do.
That's what they did?
Yeah.
If it's fairly constant, but in this particular reaction, the net reaction is this. It's 2 NOs plus Cl2 yields 2 NOCLs. Now, if they're saying this is constant, then there's no reaction. Right? I mean, how could there be any reaction if the product concentration is constant? And so you get an NR here. So it's wrong, basically. Uh-huh.
Why do I do like 4 molecules react like collide? I still get the right answer. Like the one that you say is not, so it's still wrong.
No, if you get 4 molecules, you could still get the right
Right.
answer, but don't say the right answer.
Like the same rate law. I mean the same rate.
You say the same. You don't say it's the right answer. You would say it is consistent. Okay, now somebody's going to say, okay, what's better, 2 bimoleculars or a 4-molecule collision?
2 is better for 4, but like.
Well, just in terms of probability, how often do you find 4 molecules colliding at the exact same?
But that's a slow
But it's
step,
low.
right? It's very, very slow.
It's
very, very
But it's not
even it's 4, it's impossible. Like,
It can happen, yes. It'll be very slow.
that's the what
Right. But here it's 2, and it leads to the same And so what would be much more probable?
This one,
Yeah.
but on the test, we
On the test, if you do a four-molecule collision, you're not gonna get as many points. That's for sure. Even if the that's because on the test there would be an alternate pathway, which would be more probable. Okay, other questions? And no other questions? Okay, let's talk about thermodynamics some more. We're going back to this, the state function. Now, kinetics deals with the path. And so rather than writing energy level diagrams like this, we write diagrams like this showing, how do we get from this state to that state? These reaction coordinate style diagrams. But we're going back to just focusing on this here. And typically, you would think highly exothermic reactions should be fast. Right? A lot of energy released. But, they're two separate topics. Speed, you can't always assume it's going to be fast. Because highly exothermic reactions could be quite slow. For example, the combustion of methane. Combustion of methane is highly exothermic. Is there a driving force? Yeah, for combusting, there sure is. The delta G is quite negative at room temperature. But do you see it combusting? No, it's combusting very slowly. The same thing with combustion of paper. Paper will burn in air, right? And that's highly spontaneous at room temperature, but it's a very slow process. It takes time. So if you look at very old books, the paper looks like, it's yellow, brown to black because it's slowly being oxidized, burned in air. All right. Let's take a look. I'm going to do here. So we're going to continue with
data on performance according to.
We're going to. Let me do something really quick here, sorry. Look at things that can influence the driving force for a particular reaction. Delta G, we know. Delta G is equal to delta H minus T delta S. And so one thing that can change the driving force is altering the temperature. Sometimes we can make a reaction more or less spontaneous by altering it, and sometimes we can reverse the driving force entirely. But reversing the driving force entirely doesn't happen for all reactions. Although we can always calculate a temperature, we have to look at what that particular temperature means in terms of things. So let's take a look. So the temperature, for when delta, we got this equation. When delta G is equal to 0, then we know
it's going to transition from, let's say, positive to negative or negative to positive, which is equal to delta H minus T delta F. And therefore, solving for T, we get this equation that T is equal to delta H over delta S. You know, we have to be careful because sometimes we get a situation where the T is less than 0. If the T is less than 0, what does that mean? It's impossible, right? If the T is less than 0, this is impossible. And so sometimes I ask people, at what temperature will this reaction go from non-spontaneous to spontaneous? And some people will calculate it, a temperature of minus, but they didn't realize that this is an impossible temperature. You can't have that temperature, right? And so it just doesn't work. All right. What else can change the driving force is changing the concentration or changing the pressures. So if we look at that, how do we do that? Because normally our data is for this. Our data has these little things here. I mean, they don't have to. If we have data under non-standard conditions, that's fine too. Under non-standard conditions, we don't write that little superscript there, and we get this equation. You know, delta G under non-standard conditions is equal to delta H under non-standard conditions minus T delta S under non-standard conditions, right? And so what that means is that we need this. We need these values under non-standard conditions. The problem is Appendix D is limited. Appendix D only has standard conditions. So non-standard conditions. Which would leave us stuck. All standard. And so we aren't going to be entirely stuck because there is a way to determine delta G under non-standard conditions from delta G under standard conditions. And the way we determine that is by using this equation. Sorry. And the equation is this. Delta G under non-standard conditions is going to equal delta G under standard conditions. And then what we do is we apply a correction to this. So we know what the delta G under standard conditions is, and the correction is going to look like this. It's just going to be plus RT ln of Q. And so basically what we have here is Q. We can see what's going on with the Q. Q is the reaction quotient. Reaction quotient that we saw before. And the reaction quotient is just going to be, what is the reaction quotient equal to? It's just Q is equal to concentration of G to little g, concentration of H to little h, dot, 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 over the concentration of A to little a, B to little b, dot, dot. These are just your initial, your given values. And so we've calculated the reaction quotient before. And so basically it's going to just say this. If Q is greater than K, then what does that mean?
if Q is greater than K, it means
Not really.
And there's a reaction.
Reverse. You have too much product. If Q is less than K, and if Q equals K, then it's equilibrium. And so in terms of driving force, the bigger the Q, the more product we have. The weaker the driving force should be, or the stronger the driving force should be? The weaker. And so here, as Q grows bigger, temperature is positive, R is positive. That means delta G is going to become more positive. And so this is the correction that we place on this here. Under standard conditions, what is K? All right. Under standard conditions, all concentrations equal 1 molar. Right? All pressures equal 1 bar or atmosphere. Under standard conditions. And so this is going to have some impact on this. So let's actually, probably the easiest thing to do is let's take a look at an application of this right now. One of the applications we'll see is this. If we go to H2O liquid goes to H2O gas, we saw that the delta G for this under standard conditions is greater than 0, and we said it's non-spontaneous. We had different choices, that we could do. For example, one thing that we could do was to increase the temperature. If we increase the temperature, it becomes spontaneous. And so option A was increase the temp, it becomes spontaneous. And we calculated the temperature, which becomes spontaneous, because the temperature was just equal to, delta H naught over delta S naught, which came out to something like 370 Kelvin. Is that right? Okay. Alternatively, we could go under non-standard conditions. And so B, we could try non-standard conditions. The non-standard conditions would be this. We would go to delta G is equal to delta G naught under standard conditions plus RT ln of Q. And so here we know what delta G naught is at 298. And so we're going to do this at 298 Kelvin. Temperature, this will be at 298 Kelvin. And Q, this is going to be at 298 Kelvin. So everything's going to be at 298 Kelvin. We're just going to try going non-standard here. All right, what we want to do is our current delta G is this. Our current delta G is, what was it? Does somebody have it from last time?
.5.
8.5 kilojoules?
Yeah.
our current delta G is 8.5 kilojoules. So what we have to do is we have to adjust Q. You know, we have to adjust Q to cancel out this term here. And if we cancel it out, then delta G, the 8.5 minus 8.5 would cancel it out and make this 0. And then if we make it even bigger, it'll make it negative. And so what we want to do is we want to make delta G equal 0, which is going to equal 8.5 kilojoules plus RT ln Q. Well, if delta G is equal to 0, is there any driving force? We call this equilibrium. Here. No driving force. And Q, therefore, if we're at equilibrium, Q becomes K EQ. And so what we end up with is this, that we'll get the 0 is equal to 8.5 kilojoules plus RT ln of K. And this is the thermodynamic equilibrium constant, EQ. And then we're going to solve for K and see what it means. So here, KEQ is equal to E, just rearrange this, the minus 8.5 kilojoules over RT. And so probably the easiest thing to do is convert from kilojoules to joules. So we're going to go minus 8,500 joules over R. R is 8.3145 joules per Kelvin. This is all per mole, times our temperature, 298 Kelvin. And so Kelvins cancel, joules cancel, and this should be E to that. And so KEQ is equal to, what is it equal to?
Zero point zero three.
0.0323. All right, now what is KEQ for this reaction? H2O liquid goes to H2O gas. Well, KEQ will equal the activities of the products minus the activities of the reactants. And so looking at the product is a gas here. And so that would be the partial pressure of H2O gas. And then the reactant would be the activity of H2O liquid. What's the activity of H2O liquid? 1. And so this turns out just to be the partial pressure of H2O gas here. So what this means is this. And unfortunately we don't have a demo here. But normal atmospheric pressure is 1 atm. It's normal. And so under standard conditions, you know, we're going to have to heat up the water to 373 Kelvin to get it to start to boil. But what we're going to do is we're going to hook up the water to a vacuum pump. And then what we're going to do is we're going to decrease the pressure in here. This would be called the external pressure. If we decrease the pressure to 0.323 atmospheres or less, then what's going to happen to the water? The water will start to, vaporize spontaneously at room temperature. In other words, water will boil at 298 Kelvin if P external is 0.0323 atmospheres. And so that would match the vapor pressure of water coming up here. And water should spontaneously boil. Right, but our vacuum pump is not strong enough. Do you think is this vacuum very strong? No. This vacuum is not very strong. What do you think this vacuum is? I'm going to max it out. Maybe I'll be generous here and say this vacuum is maybe a half an atmosphere. What do you think? Okay, let's just say if the vacuum is 0.5 atmospheres, will water boil at room temperature? No. But will it boil at a lower temperature than 373? Yes. And so what we could do is we can help this. We don't need as much heat if we have some vacuum. And so if the vacuum is 0.5 atmospheres, at what temperature will water boil? All right, so why don't you try to figure that out? Well, since we don't have that much time, let's see. This is going to be standard or non-standard conditions? Non-standard. So we need delta G non-standard. And we know delta G non-standard is equal to delta G under standard conditions plus RT ln of Q. Now, right now, it should be non-spontaneous, right? Delta G should be positive. And so we're going to use a combination. We're going to use a combination of temperature and non-standard conditions to do it, right? And so doing that, we want delta G to equal 0, which equals delta G naught plus RT ln of Q. So we want, these two terms to cancel each other out. This is non-spontaneous. We want to make it spontaneous. In other words, delta G naught is equal to minus RT. Now, ln of Q gets changed to K. And so we do this. We just solve for T. That is, T is equal to delta G naught RT ln of K. Oops, yeah, just R. R ln of K. Here. Right? And then we know that K is equal to the partial pressure of H2O gas, which is equal to 0.5 atmospheres. And so at what temperature will the partial pressure of H2O gas equal 0.5 atmospheres? And if I have a vacuum, so the partial pressure is 0.5, the P external is 0.5, it should boil, right? And so let's go ahead and solve this then. That is, T is equal to minus, what was delta G again? 8.5, right? 8.5 kilojoules over R, 8.3145 joules per Kelvin. This is all per mole. ln of 0.5. We have to convert it, probably just convert it to joules, 8,500 joules, 8.3145 joules per Kelvin. LM 0.5, which is what, minus 0.693 or something. What does the temperature come out to? Okay, 1,000? 474? 1,474 Kelvin? Wow, it's big.
That's
Hmm?
more than that.
What?
Shouldn't the temperature be lower than
The temperature should be lower. But is the calculation right? Unfortunately, the calculation's not right. What's wrong with this calculation? It should be lower, but you know, I made a big error. Do you know what my big error was? I made a huge error in this calculation. No, K is 0.5. We're setting it to 0.5 because we want to figure out what temperature it's going to. In fact, you know, delta G is related to K. Do you see the relationship between delta G and K? It's right here. And so this shows the relationship between delta G and K. What could be wrong? Does anybody see what I did wrong? It's hard to see what I did wrong. You know, it's hard to see what I did wrong because you know, usually you don't write this kind of stuff here. What I did wrong was this. What is this delta G naught at? What temperature? This delta G naught was at 298 Kelvin. Right? I need, you know what I need? I don't need the delta G at 298. I need the delta G naught at the temperature I'm trying to solve for. Well, how can I determine the delta G naught at the temperature I'm trying to solve for when I don't even know what the temperature is? Right? And so do you see this is an impossible equation to solve? Because the only way I could solve this is by making this assumption. I had to assume that delta G at temperature, delta G naught at temperature T is equal to, or about equal to, delta G naught at 298 Kelvin. That's the only way I can solve this problem. Is this assumption correct? No, this is a bad assumption. Because delta G changes significantly with temperature. I mean, we could even make a non-driving force into a driving force just by altering the temperature. And so this is all wrong. And so we need to figure out an alternate route to what we're after. And the alternate route to what we're after is right. Actually, yeah, what if we do that? Rather than doing that, we say, okay, we do this. We set this equal to minus delta H naught minus T delta S naught.
Does that work? Over R ln of K. That works, but this is a weird equation because we're trying to solve for T, and T's over here too.
No,
Right.
We took a step behind. And then we could
Yeah, actually, let's take a step behind because this is going to be kind of difficult too. And so if we go back and
Multiply by
multiply by what?
like R, L, and K become T, and then we use T delta S over and take T out.
All right, we could do it that way. We do it that way? Or we could do it a step back. All right, so we're going to get T, R, actually, we'll just call it RT. RT ln of K equals delta H naught minus T delta S naught. And then we have to do the negative for this whole thing, right? And then let's add a delta H naught to both sides. Do that?
No, T
Let's add
delta
or
S.
let's subtract
the
the
T
T
delta
delta
S.
S from both sides.
And then
Factor
Then we can factor out.
Okay. So we add the T delta S or subtract the T delta S from both sides. So we're going to get RT ln of K minus T delta S naught, which is equal to negative delta H naught. And then factor out a T here. And so we're going to get T R ln of K minus delta S naught, which is equal to minus delta H naught. And therefore T is equal to minus delta H naught over R ln of K minus delta S naught. Okay, does that work? Yeah, this seems to work because here we can make the assumption that delta H at temperature T is about equal to delta H at 298, and delta S at temperature T is about equal to 298. And so now this is okay. Your book is going to do a little differently because your book is going to get rid of this, or distribute this negative in here. Just flip these. You know, if I change this to a positive and flip these, then it'll do the same thing. But you see the point here. The point here was this. This is bad. This is okay now. And so now we can do the calculation. But we also have to calculate delta H at, and delta S. All right, there's one more equation that we'll be using here, and that is this relationship between delta G naught and K. We can derive in a different way, and then we can come up with another equation. And yeah. It's the ln of K2, except this K is for the equilibrium constant K. Actually, let me give that to you here in the same form as the book. Let's see, do they do it for delta G or do they do it for delta H? They did it for delta H. We could have let's do it this way. Let's do it for delta G. And so what I'm going to do is, I know that delta G naught is equal to minus RT ln of K, you know, when delta G is equal to 0. Does that make sense for this equation? Okay, now let's solve for ln of K. ln of K is equal to delta G naught over RT negative, correct? Now let's use our trick. What's our trick? This is going to be K, the equilibrium constant, 1 at temperature 1. If I change the temperature, the equilibrium constant changes, right?
And so my trick is going to do this. Ln of K2 minus Ln of K1 is equal to minus delta G naught over RT2 minus delta G naught over RT1. And therefore I'm going to get this equation. Ln of K2 over K1 is equal to, I'm going to factor out the delta G naught and R. So I'm going to get minus delta G naught over R, 1 over T2 minus 1 over T1. Does that equation look good? Mathematically, it seems okay because that's our trick, right?
But you just said a G, you cannot apply that temperature.
Right. So that's good. You recognize that this is impossible. Why is it impossible?
Temperatures are changing.
Because the temperatures are changing, but delta G is not. Right? So this is this doesn't work. But just like the previous trick we did, we could get delta G not in terms of delta G, but in terms of delta H and delta S, which do not change that much with temperature. And so what we need to do here is we need to back up. I'm going to back up and redo this like this. And so if we say that delta G naught is equal to delta H naught minus T delta S naught, that's true, right? And delta G naught is also equal to minus RT ln of K. Okay, now how are we going to do this?
So for K, Ln K,
Okay, solve for ln K. Ln of K is equal to
delta H naught
delta H naught
minus T delta S naught divided by
minus T delta S naught divided by
negative RT.
negative RT.
And then rearrange like the other one.
Okay, so this would equal delta H naught minus RT
Yeah,
plus
delta S naught divided by R.
delta S naught divided by R. Now we're going to apply the trick here. And that is ln of K2 minus ln of K1 will equal delta H naught minus delta H naught over RT2 plus delta S naught over R, okay, minus K1, which would be a minus delta H naught over RT1 plus delta S naught over R. Now delta S naught over R is the same reaction, just a different temperature. So delta S and delta H should be the same. And therefore this term cancels out and we get this. We'll factor out the delta H naught over R. So we get minus delta H naught over R, 1 over T2 minus 1 over T1. Does that work? Yeah, this works as long as we can assume safely that delta H naught at T2 is about the same as delta H naught at T1, which is an okay assumption. And therefore we get this. This equation is going to be ln of K at temperature 2, this is the equilibrium constant, not the rate constant, over K at temperature 1 is equal to this.
Wouldn't it be plus 1 over T1?
I'm sorry?
Wouldn't it be plus 1 over T1?
No.
But the delta H is negative. And you distribute the negative sign in the front.
Oh.
No, you factor out delta H.
Yeah, I factored out the negative delta H, so it's still minus 1 over T1. So do you see this? Even though this equation looks very similar to the Arrhenius equation, the Arrhenius equation is a little different because Arrhenius is the rate constant, and activation energy. This is the equilibrium constant, and delta H. And so what this allows us to do is allows us to figure out the equilibrium constant at any temperature. And so this would have been a useful equation to have in chapter 15.
we could have figured out how the equilibrium constant changes with temperature, but we had to wait until chapter 19 to see it. Okay, I'm going to stop here because I'm over time, but that's it.